Morning, everyone. Give me just a second. I think I had to update your syllabus on Moodle last night, and I think I gave you the 151 syllabus, and that is not what you want. So let me adjust that. Okay, much better. So this okay. So this next chapter that we're working on is, I'll just share the screen, is chapter 6, which is ionic and molecular compounds. So we're gonna be working on it this week, and we're gonna be working on it a little bit next week. So because of that, you won't have a mastering chemistry due this Sunday. That's why, because we haven't completed the full chapter. So this whole chapter, it's an important chapter. It's about naming, specifically making compounds and naming compounds that are inorganic. So yeah, it's kind of like you can't get the full chemistry experience. You can't do ladder things in this class if you can't name things properly. Oh, we don't want chapter 4. There we go. So this is chapter 6. So we're skipping chapter 5 for now, which is nuclear chemistry. We'll come back to it, but we'll do that a little bit later. All right. So as of right now, you guys should be good with atoms and the periodic chart. So it's kind of like at this point, you know the letters of the alphabet. And now we're going to start putting those letters together to make words, because how often do you use just a single letter? I, A, right? But in general, we tend to use words to describe things. It's the same thing in chemistry. You don't often see elements in nature existing by themselves. You see them mixed with other things. They're not even mixed, bonded with other things, because they're much more stable when they're in a compound form. So this will look at ionic and molecular compounds. And we'll get into how to name those and everything. So the first thing is to talk about what we classify as ionic, or what is in an ionic compound. So an ionic compound has ions in it. And an ion is just an atom that has either a relatively positive charge or a negative charge. It has a positive charge if it has gained electrons. Or I'm sorry, it has a, I don't know where my brain is today. It has a positive charge if it's lost electrons, it has a negative charge if it's gained electrons. So think of the electron again as that negative friend in your life, or negative person, or negative thought. The more of those negative things you have, the more negative you become. All right. So ionic bonds are formed where you have a positive ion, like let's say this Na, and a negative ion, like this Cl minus, and they stick together, just like a positive and a negative side of a magnet would stick together. So ionic and covalent bonds, when we talk about a chemical bond, we're talking about something happening with the electrons, specifically the outermost electrons or the valence electrons. When an atom loses, gains, or shares valence electrons, they're always trying to get to what we call 8, or the octet rule. So 8 valence electrons minus a duet or 2 for the very, very small ones like hydrogen and helium. Everything else wants to have 8 valence electrons because that's a stable configuration. It's a full onion layer in its outermost electron shell. There's 2 different ways that you can get to this octet or this 8. In an ionic bond, things will gain or lose electrons to get an octet. Now, looking at your periodic chart, everything in the last column, so the noble gases, those already have an octet. All of those have 8 valence electrons, because remember, the number of valence electrons is dependent on whatever row, column you're in, number-wise. So the last one, all have 8, they're particularly stable. So everything is sort of trying to get the electron configuration of a noble gas. So in an ionic compound, something can gain or lose an electron to become like a noble gas as far as its electron configuration is concerned. Think about chlorine. Chlorine's number 17 on the periodic chart. What charge did you put above that column? Hopefully you put a -1. If you're a -1, what does that mean? It means you're eating an electron or you're taking an electron on. So if we add an electron from onto chlorine, what does your configuration become like? Oh, you become like argon, right? So now you have upped the number of electrons to be like a noble gas. Let's see if there's, yeah, we've got it over here. Talking about. So everything is going to gain or lose electrons to get to this noble gas configuration. So chlorine gains an electron to become like argon. Oxygen gains 2 electrons to become like neon, right? Sodium, on the other hand, has to lose an electron to become like neon. Could sodium gain 7 electrons? I mean, 1, 2, 3, 4, 5. It would need 6, 7. There's 2 more in there to become like neon. I mean, I guess in theory you could force it to do that, but that it's much more practical for it to just ditch that outermost electron to become like neon. So the other type of bond that we have is a covalent bond. Covalent bond, sometimes called molecular, that's where the electrons are being shared. Okay, rule of thumb, ionic bonds are going to be between a metal and a nonmetal. So a metal smushed with a nonmetal. So like here we've got sodium, which is a metal, combined with chlorine and nonmetal. Covalent bonds will happen between 2 nonmetals, so 2 things on the right side of the periodic chart. In this case, they're going to share electrons in order to create a stable electron configuration. And when I say stable electron configuration, I mean they're going to share electrons in such a way that each of them has access to 8 electrons. Because again, it doesn't matter whether it's done through ionic or covalent, they want to get to 8 electrons. So here is an example, a visual example of an ionic. We've got molecule M or atom M and atom NM. What we can see here from our dot configuration is this one has 1 valence electron. Over here, this NM, it has 7 valence electrons. Well, if this electron just moved over here, what would happen is this would have 8 valence electrons. And then M would also have 8 valence electrons. They're not drawn in, but think about the onion layer that sits below this valence electron, right? It's a complete onion layer. We always complete the lower onion layers and build out. So if we strip this away, then we've got a complete electron configuration underneath. So this will form a plus charge, this will form a minus charge. They both have valence of 8. And now they stick together. So the plus and the minus bonds them together in this ionic bond. That's different than what's happening if we have 2 NMs. Here, this has 7 valence electrons and this has 7 valence electrons. Transferring wouldn't work because if this electron went over here, this guy would have 8, he'd be happy, but this guy would be down 1, he'd have 6. He'd be even less happy than he is right now. So instead, what they're gonna do is these two are gonna share these electrons, or they're gonna kind of throw them in the center. So if we throw these two in the center, this one has access to 8, and this one also has access to 8. These two in the middle are being shared. So they're kind of in a no man's land where they can, either one can access them. This we would call a covalent bond. So positive ions, metals like to form positive ions or cations. Group 1A, group 2A, and group 3A have very low ionization energies, meaning that it's really easy to lose that first electron. They're going to lose electrons to get to a noble gas configuration. So sodium, which is in group 1A, it has 11 electrons and 11 protons. If it loses an electron, it will form the noble gas that comes before it. So look at sodium, what comes right before it on the periodic chart, kind of read backwards. You see that it is neon. So now it has the electron configuration of neon. So above column 1, there's a +1. Magnesium has to do a little bit more work, right? Magnesium, it's not going to hop forward to argon. It's not going to gain that many electrons. It's going to lose 2 electrons. If magnesium lost 1 electron, let me go here. If magnesium lost 1 electron, it would become like sodium. So it's going to lose 2 electrons because, again, everything wants to become like neon. So above column 2, we have +2. These guys form predictable +2 charges. What about, what do we got here? So that's magnesium. Let's look at something on the other side of the periodic chart. So chlorine, which we've kind of already talked about. Chlorine has 7 valence electrons. So here's its little Lewis structure or dot structure. It's so close to having an octet. What it's going to do is grab an electron and form a solid octet with a negative charge, right? Because it's eaten 1 electron. It's up an electron and it's much more stable in this fashion. So above fluorine, chlorine, bromine, iodine, column 7, you want to make sure you have a -1 because those like to form a -1 charge. So here are all the predictable charges. So over column 1, minus hydrogen, you put a +1. Over column 2, put a +2. Where aluminum is, which is column 3, it doesn't include boron because boron is a nonmetal, but aluminum and also gallium underneath it, those form +3s. Go over to the column where nitrogen is. Nitrogen and phosphorus, those form a 3- charge. So if you don't have that written above that column, do so. Oxygen and sulfur, you're going to put a 2-. Fluorine, chlorine, bromine, iodine, above that column, put a 1-. And then above the noble gases, again, just put a strike, a 0 with a strike through it, because those don't form a predictable charge. So hopefully it's making a little more sense why lithium always forms a +1 charge. Like would you ever have Li2+? No, because if you did that, you'd go to helium and then you'd just become like hydrogen, the thing before it. So you'd blow past the noble gas. We always want to land on the noble gas. Same thing with, fluorine. Fluorine here. Fluorine's never going to be F3- because that would mean it'd go to neon and then it'd blow past neon and become like calcium, right? Take 2 more hops. Also, you'd never see fluorine with like a 3+. Because that would mean it's losing 3 electrons. It's going oxygen, nitrogen, and then what's missing here, carbon. It's never going to do that. That doesn't make sense. So these main group elements have very predictable charges. Couple other that I want you to write. So find aluminum on your periodic chart. I don't know if I told you this already, but where aluminum is, that's a 3+. Go down and to the left where zinc is. Zinc, you want to write a 2+. So put a 2+ in that little box. And then go down into the left. Silver is a 1+. Okay, so 3, 2, 1, down into the left. Zinc and silver are sitting in the transition metals, that middle area where their charges are more varying, but they do have a predictable charge. So zinc will always be 2+, silver will always be 1+, and that is important because it determines how we name things. Ions are important to regulate body function. So it's not just that we need to have sodium in our body, but we need to actually have the sodium ion in our body with that positive charge. You can find it in salt and pickles and cheese. It helps to regulate body fluids. Again, we need to have potassium plus, the ion, calcium 2+, and magnesium 2+. That charge helps to regulate a lot of systems in the body. So it's not enough. That's why we don't eat like sodium as a metal in its metal form. How do we get sodium? We eat it through sodium chloride so that we get the ion. All right, so write the formula and symbol of an ion that has 16 protons and 18 electrons. So why don't you try and do this? So you will write some sort of symbol X. I'm not going to tell you what it is. And then in the upper right-hand corner, you're going to put a charge. Okay, so if it has 16 protons, well, the only option is sulfur because that's 16 protons is synonymous with sulfur. It has 18 electrons. So your charge is going to equal protons minus electrons always. So if I have 16 protons and 18 electrons, well, the electrons are winning out, right? The negative particle, there's more of them by a factor of 2. So it's -2 or 2-. So the charge should be 2-. So it's sulfur with a 2- charge. Does that make sense with what we know of sulfur and oxygen in that column? Yes, it does. Hopefully you have a 2- above there. I want you to do another one of these. So let's say we've got, okay, so protons are 15 and electrons are, no, yeah, we'll do it anyway. 15, 18, it's an 8, sorry, I don't have my pen. Do that one, and then I want you to do another one. Protons are 23. I don't know what is going on with my pen. I'm going to do this somewhere else. This isn't working for me. Come on, how long does it take to open? just gonna read on this one. All right, so protons are, what did I say, 15, and electrons are 18. And then another one, I'm gonna do protons are 25, and electrons are 22. Okay, so write a symbol, like I said, some sort of a symbol with its given charge for that. So if we have 15 protons, we have to be phosphorus. Now you can look at your periodic chart and say, okay, phosphorus always has a 3- charge. If you wanted to go a step further, protons minus electrons. So 15 minus 18 gives me a -3 charge. This one here, we've got protons are 25, so that's manganese, which is Mn. You can't read the charge off of the periodic chart because it's in the transition metal area. So we do actually have to calculate it. So protons minus electrons in this case, or 25 minus the 22, which is 3, but a +3. So we're going to say 3+ for that one. When talking about charge and things like that, we don't bring into play neutrons. Okay, neutrons we kind of leave for isotopes. Electrons have to do with charge. So consider the elements calcium and chlorine. I want you to identify them as a metal or non-metal. Tell me how many valence electrons there are for each. Tell me how many electrons would be gained or lost for each. And then write the symbol with its charge. So we have calcium and we have chlorine. And this will make a little more sense why we're doing this in a minute. All right, so calcium is our metal. In this case, chlorine is our non-metal. The number of valence electrons, well, calcium is in column 2, so it has 2 valence electrons. Chlorine is in column 7, so it has 7 valence electrons. Remember, whatever group it's in is the number of valence electrons. Calcium is going to lose 2 electrons. So you have it also in column 2, and you have a 2+ above that column. So it likes to give up 2 electrons. So there's 2 different things happening within each column, right? There's the number of valence electrons, and then there's the number of electrons it would like to gain or lose. So don't confuse those numbers. Sometimes they're the same, right? If you're in the second column, you have 2 valence electrons, and you give up 2 electrons to have a 2+ charge. But if you're in column 7, like where chlorine is, You have 7 valence electrons, but you like to gain 1 electron to become a -1 charge. You've got to be able to do that, okay? That is the basis for writing chemical formulas that are ionic, is to be able to find and or pull out the charge with its symbol. So let's talk about how you get to writing a formula for an ionic compound. So why is sodium NaCl and not like Na2Cl5? Why is it a 1-to-1? Well, ionic compounds consist of a positive and a negatively charged thing that are held together by this electrical attraction. Those charges need to equal each other. So the positive ion has to be equal and opposite in magnitude to whatever the negative ion charge is. They tend to have high melting points and are solid at room temperature. So if you have salt, right, and it happens to spill on your hot stove top, the salt's not going to melt, right? If you happen to drop butter on your hot stove top, it'll melt very quickly. But an ionic bond has a very, very high melting point. So sodium chloride, this NaCl, which we call table salt, if we were to look at it up close, we get this repeating patterns of NAs and Cls and NAs and Cls in this 3-dimensional lattice structure. That's what ionic compounds do. So they're not individual molecules. It's not like it's one Na mixed with one Cl, and the NAs and the Cls are just sort of smushed together. They're actually forming this 3-dimensional lattice structure. This gives it a very crystalline shape, and you can actually see that on a macroscopic scale where you see salt growing these crystalline shapes. So when writing a chemical formula, the chemical formula will represent the atoms that are present and their lowest whole number ratio. So because it's a lattice structure like this, right, it's not actually that you have one Na and one Cl bonded. You've got an Na and a Cl and an Na and a Cl repeated in a pattern. So when we write an ionic compound, we just want to write its lowest ratio. So how many Nas in it for every Cls? Well, this sodium has a single valence electron, so it's going to want to lose that valence electron or form a +1 charge. Chlorine has 7 valence electrons. It wants to eat that electron. So this is going to move over here. This will have a complete shell. This will then have a complete shell. This will have a positive charge and this will have a negative charge, and they stick together. 1 sodium at a +1 charge, 1 chlorine at a -1 charge, it balances out to a 0 charge. Whatever the positive charge is and the negative charge has to equal a neutral charge of 0. So it's like, how many of the positives and how many of the negatives do you need to balance out? What if you have 2 negative friends? How many positive friends do you need to neutralize that? You would need 2 positive friends, right? What if you had 3 negative friends? You'd need 3 positive friends. So you need to make sure that the sum of those 2 are charge balance or charge neutral. Magnesium likes to form a 2+ charge, right? We said magnesium Mg2+. Chlorine only forms a -1 charge. So I can't take 1 magnesium and smush it with 1 chlorine because there'd be an extra positive charge, or this magnesium wants to give 2 electrons away. If the chlorine only wants to accept 1 of these electrons, well, somebody has to accept this other electron. So another chlorine is going to accept that secondary electron. So your formula for this will actually be 1 magnesium with 2 chlorines, or MgCl2. Because the magnesium has more to give than just a single chlorine can accept. There's kind of and so when you calculate it out, right, if you have a magnesium with a 2+ charge and you have only 1 of them, that gives me an overall 2+, right? If you have chlorine with a 1- charge, but you have 2 of them, that gives me a 2- charge. This plus this equals 0 for charge neutral. Now, do I expect you to write out these drawings every time you do this? No way. This is like way more work than it needs to be. There's a really fast way to figure out how to get charge neutrality. Okay. Here's another example. Okay, so the positive charge has to equal the negative charge. Sodium wants to give up 1 electron. If it's mixing with sulfur, well, sulfur doesn't want just 1 electron. It wants 2 electrons because it has 6 valence electrons. So it actually needs 2 sodiums to fill in that empty void. The sodiums have a plus charge. The sulfur has a 2 minus. 2 of the positives plus 1 of the 2 minuses will balance each other out. How do they don't even teach it with the flip-flop, which is so silly. Okay, so the fastest way to do this is to flip-flop the magnitude of the charge with the subscript of the opposite guy. So I would say if we're mixing barium and chlorine, write the symbol for barium with its charge, and then write the symbol for chlorine with its charge. In this instance, they're not bonded together yet. They're just 2 ions floating around in space. So you're going to take not the charge, not if it's positive or negative, but just the number, just the magnitude. Okay, so this has a 2. And then what do we have over here? There's an inferred 1, right? We just haven't written it in. A minus charge is a 1 minus. So the charge on the first thing is going to become the subscript on the second thing. So the magnitude of the charge. So this number is going to become the subscript of the nonmetal. And this is going to become the subscript of the metal. Or we flip-flop. So this tells me that I've got 1 barium, Ba with a 1. You don't have to write the 1. This 2 tells me I'll need 2 chlorines to balance it out. It's the fastest way to find the lowest common denominator. If you want, you can go back and check. So what is the charge on barium always? Barium always has a 2 plus charge. And how many are there? Well, we said there are 1 for a total of a 2 plus. Chlorine has a 1 minus charge, right? 1 minus, and how many do we have? In this case, you have 2. So this forms a 2 minus. What happens when I add these 2 things together? I get 0, right? Equal to 0. Do I expect you to like balance them out every time you write a formula? No, but you may want to do it in the beginning just to make sure you've gotten it correct. So I think the flip-flop is the fastest way. So let's do a couple other ones. Ooh. So I can, now that I know the flip-flop rule, I can do really any, or not any, but a good amount of formulas. Like let's combine a couple things. Let's combine potassium and nitrogen. So I'm not giving the correct name for this yet. The correct name would be potassium nitride, but let's do formulas first. So potassium, easiest way to do this. Well, first thing you want to do is decide, is it ionic? Yes, this is in fact ionic. So I do want to balance charges. If it was 2 nonmetals, you don't want to do this, all right? If it was oxygen and nitrogen, you wouldn't want to do this. It has to be one thing that forms a positive charge and one thing that forms a negative charge. So potassium is a metal, so I'm going to write potassium with its charge. Nitrogen is a nonmetal, and I'm going to write its charge. Where am I getting these numbers? Again, they have predictable charges, so just make sure you have that above the columns. So now we're going to flip-flop. So here there's an inferred 1. So the 1 is going to drop down to the nitrogen, the 3 is going to drop down to the potassium. So K3N with a 1. We don't need to put the 1. This is the formula for potassium mixed with nitrogen. You can go ahead and double check. Potassium always has a 1 plus charge, and there's 3 of them for an overall 3 plus charge. Nitrogen always has a 3 minus charge, and there's 1 of them for an overall 3 minus charge. 0, neutral. What are some pitfalls that I see people do? I'm gonna write over here in red the things that I don't want you to do. Some people will, instead of flip-flopping, so instead of taking this number and dropping it to the opposite guy, they'll just drop it straight down and they'll say, oh, I get 1 potassium for every 3 nitrogens. You see how that happens? They drop it down directly. You don't want to do that. And I'll show you right now why that doesn't work. What's the charge on potassium in this formula? It's always 1 plus. How many do I have in this formula, the way it's written? I have 1 for a total of 1 plus charge. Nitrogen has a 3 minus charge. How many do I have in this formula? 3 for an overall 9 minus charge. Oh my goodness. What is our overall charge here? 8 minus. Is that neutral? No. So that's definitely don't want to just drop them down. You need to flip-flop. Let's see some other things that students do. They don't even write the charges. They just get, or they will write the charges, but then they don't use them and they just say, oh, Kn. It's potassium smushed with nitrogen. There are potassiums and there are nitrogens, but because it's a metal and a non-metal or ionic, you've got to charge neutralize these. In this case, it's not charge neutral. Potassium has a 1 plus. In this formula here, there's 1 of them. That gives you a 1 plus charge. Nitrogen is a 3 minus, and you have 1 of them. That's an overall 3 minus charge, 2 minus, not neutral. This does not work either, okay? Other things I see students do, quite often, let's see. So they ditch the charges, they don't flip the charges. Oh, they do things like this. When the ion is by itself, it has a charge. When it's combined, it's neutral. So there isn't a charge in this upper right-hand corner. Why has the charge disappeared? Because the metals are balancing the non-metals. What I see happen sometimes is students they'll do the right thing, they'll flip-flop. So they'll get K3N, and then they'll want to put that 3 minus charge in the upper right-hand corner. Or they'll put the charges in the corner and it'll be like something like this. No, these go away when they've bonded together, no charges, okay? That's something I see. So when we're looking at a material, like I'm gonna put a polyatomic ion on here, SO4, 2 minus. It's important to know what's a subscript and what's a superscript. So anything below this sort of half line is a subscript. This is talking about number of atoms. Anything above this dotted line, this is charge. So when looking at this thing, which is a polyatomic ion, which we'll talk about a little bit more, I have 1 sulfur, I have 4 oxygens, and the whole thing has a 2 minus charge. Don't want to get those numbers mixed up. Any questions on flip-flopping outside of the fact that we need to practice? All right, I'm going to give you some. So I'll give you 2 things, and I just want you to combine them into a formula. So I want you to take aluminum and bond it to oxygen. I want you to mix silver and mix it with, bond it with phosphorus. And then I want you to do barium and mix it with oxygen as well. I'll give you all 3 minutes for that, 1 minute each one. Okay. So again, before you even like try and do this, you always want to just quick double check, is it a metal and a non-metal? Because if it's not, then this is a pointless exercise. So this is a metal, this is metal, this is metal, and these are all non-metal. So this flip-flopping will work. So write the symbol of the metal, that's aluminum, and then its charge. Aluminum always likes to form a 3+ charge. Oxygen, non-metal with its charge, it always likes to form a 2-. Those charges don't change. So there we're going to flip-flop. So I should have 2 aluminums for every 3 oxygens, right? This goes here, and then this goes here. Take the magnitude, drop it to the subscript. It tells you how many of each you have. Silver and phosphorus. Silver is Ag. That always has a plus charge. I know it's sitting in the transition metals, and those other transition metals have varying charges for sure, but silver will have a predictable +1. Phosphorus, which is P, will always have a 3- charge just because of where it's located. Flip flop, I should have 3 silvers for every 1 phosphorus. The 1 comes to here, the 3 goes to here. Last one, barium and oxygen. This is to show you just a simple thing you always want to do. If you get into this case, barium is a 2+, oxygen is a 2-, flip-flop, you should get Ba2O2. But anytime it's reducible, reduce it. So both of these can be divided by 2, or it becomes barium oxide, 1-to-1. Okay? So with ionics, reduce. With ionics, reduce. Questions on flip-flopping? That is the fastest way to do it. You could think, oh, well, if barium is a 2+ and oxygen is a 2-, then it should be one of these for every one of these. We'll balance it out. You can go about that way too. I just think the flip-flopping is the fastest, cleanest way to do it. Okay, so here are some more examples. Sodium mixing with oxygen. If we were to flip-flop, we'd need 2 sodiums for every 1 oxygen. So it'd be this one here. Aluminum and chlorine. If it's a 3+ and chlorine is a 1-, then I need 3 chlorines for every 1 aluminum, flip-flop. Magnesium 2+, nitrogen 3-, flip-flop. See, this is a pitfall. This is where I see students, just smush them together. We don't want that. This one, they haven't flip-flopped, right? They just dropped the 2 and the 3 down. You got to flip-flop. So we'd need Mg3 or N2. The important thing is that, right, when you go and check, all of these are charge neutral. Now, again, if you're following the system and you're getting it, you don't need to check the charge neutrality every time you do it. If you're feeling a little rusty or you're not 100% sure, that's a quick way to tell if you've done it correctly, or a self-check. So naming these things, naming ionic compounds. When I look at this thing here, this is iodized salt, which is potassium and iodine. I don't call it potassium iodine though. I call it potassium iodide. Just like sodium and chlorine, I don't call it sodium chlorine, I call it sodium chloride. So when naming things in chemistry, it's called nomenclature, which is just a fancy way of naming. It's a systematic way of naming. So there's a set of rules, because how many compounds are out there? There's like thousands and thousands and thousands. So you've got to have some sort of systematic way to name things. Like water is an everyday name. Its systematic name is dihydrogen monoxide. How do you know everyday names like water or table salt? You have to learn those. You can't learn everyone. Memorizing would be totally crazy. So we have this system so we can always name a compound. And what if in English it's water and somewhere else they call it something else? We need to have some sort of thing that we can all relate to as chemists. So when writing an ionic compound, the first thing you do is always name the metal, and you just write its name. So if it's potassium, you write potassium. If it's sodium, you write sodium. Then you write the name of the non-metal, but you just do the first syllable of it. So you cut off the end of it and you put IDE at the end. So it's not sodium chlorine, it's sodium chloride. a space is placed between the name of the metal and the nonmetal. So we don't smush it together into one name. It will be, or one word, it'll be two separate words. So looking at this one, we have potassium and iodine. We cut off the last part of it and we make it iodide. So potassium iodide. This is magnesium and bromine. We write the word magnesium and then we bromide it. Aluminum, we cut quite a bit of the oxygen off. So it's not oxygenide, right? It's oxide. So remove everything but the OX and then add the IDE. And that's it. I mean, for this section, it does get more complicated, but it's really just name the metal and then ide the nonmetal. So guide to naming, identify the cation and the anion, name the cation, which is just another way of saying the metal or the positively charged thing, name the anion and ide it. Great. So looking at this thing, we've got potassium and oxygen. So if we were to name this thing, it would be potassium oxide, and you're done. Okay, name these three things. Okay, so this first one here, metal and a non-metal, calcium oxide. Metal and a non-metal, again, you want to be just making sure, is it actually ionic? So this is aluminum and oxygen, aluminum oxide. This one here, magnesium chloride. If I was to write something like this, CO3, I would not be naming it carbon oxide because this is a nonmetal and this is a nonmetal. I could have CO3 or I could have CO2 or I could have CO. So when we have nonmetals, they have more varying possibilities because they share electrons. So we actually have to say how many of each we have. So this would not follow this system. Why don't I have to specify that there are 2 aluminums and 3 oxygens in this case? Because anytime you write the word aluminum oxide, is that enough information to get back to this formula? Yes, it is, because aluminum has a predictable charge. Oxygen has a predictable charge, flip-flop, Al2O3. I will always come up with that formula, okay? So that's why we don't have to use like prefixes or anything like that with this. All right. Oh, this is very dramatic. Okay, calcium oxide, aluminum oxide, magnesium oxide. So I want you to go through this matrix. I want you to, so we put on the y-axis, put sodium and aluminum. And on your x-axis, you'll put bromine, sulfur, and nitrogen, specifically with its corresponding charges. So you're going to go through and combine each of these. I want you to write the formula and I want you to write the name. So I can do this first one with you all. I've got sodium and I'm going to combine it with bromine. So I flip-flop the charges. It's a 1-to-1. So it'll be NaBr. And then I'm going to write its name, which is sodium bromide. And I IDE the end. All right, you're going to do it for the other 5 boxes.
Nobody's here.
All right, so in each of these, we're going to be combining a metal with a non-metal. You're never going to get like a mixture of two metals, right? These aren't, there's no box for these two to mix or these two to mix. So at least not in an ionic situation. So sodium has a plus charge. In this case, sulfur has a 2- charge, flip-flop. So I need 2 sodiums to balance out every 1 sulfur. I would call this sodium sulfide, IDE. Next one, sodium still has a plus charge. Nitrogen has a 3-, flip-flop. I should have 3 sodiums for every 1 nitrogen. So this is sodium nitride, IDE. All right, aluminum has a 3+ charge. Bromine has a 1- charge. So flip-flop, I should have 1 aluminum, and then I have 3 bromines. We would call this thing alumina. Oh, hello. Come on. Bromide, right? So in this case, all the non-metals are the same. The metal is what changed. Aluminum has a 3+ here, a 2- here, flip-flop. So I should have 2 aluminums, because the 2 from the sulfur, for every 3 sulfurs. And we would call this aluminum sulfide. And then this last one, flip-flop. Now, if I flip-flop, I'm going to get aluminum with a 3 and sodium with a 3. What do we do when we have the ability to reduce? We reduce. So this is just going to be ALN, and we're going to call this aluminum nitride. Any questions on that? If you feel confident in doing that matricy, you are good with the first 25, 30% of naming for inorganics. Great. So there they all are, written a little neater. Zinc is a 2+. We talked about this. There are transition metals with predictable charges. Zinc is a 2+, silver is a 1+. If you want, you can do cadmium too. Number 48, you can put a 2+ in that little box. But what about everything else, right? Like, what if I want you to combine iron with oxygen? Well, iron can have, like, look at what column iron is in. It's in some middle column, and I didn't tell you what charge to write because it can have a bunch of different charges. Iron could have a 2+ charge. It could have a 3+ charge. Hypothetically, with homework and stuff, it could have a 4 or 5+ charge. So you have to go a step further. You can't just write the name of the metal. You also have to include a Roman numeral, which is equal to the ion's charge in that very specific situation. So if I'm dealing with copper that has a 2+ charge, I need to write it like this: copper parentheses Roman numeral 2. If I'm dealing with a copper 1+ charge, I need to put copper Roman numeral 1. You don't negate the 1 charge. I know sometimes we ditch the 1, right? You can't do it with the Roman numeral charges. Keep that in place. If you have like lead 4+, it'd be lead IV. The I in front of the V is a 5. When you put the I in front of it, it's a subtraction. If you put the I after the V, it's an addition. So if it has a 6+, VI means 5 plus the 1. So you do need to know your Roman numerals. Do you have to have every transition metal's possible charges memorized? No, 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 no. You'll always be able to figure them out, and I'll show you how to do that. But you do need to know that if you're dealing with iron 3+, it's not enough just to say iron. You got to say iron Roman numeral 3, okay? So here are some of the varying charges of some of the transition metals. Again, don't worry about memorizing these. It won't do you any good. So let's talk about how to determine a varying charge. So if I have MnF, this is manganese and this is fluorine. So the way that I usually attack these, and this is the answer down here, but we'll go through how we got that, is I write the name of the metal. So manganese. Very common for people to mix this one up with magnesium. All right, magnesium is Mg, manganese is in the transition metals. So I'll write the name of the metal, I'll put a parenthesis there and I'll come back to that. And then whatever the second thing is, fluorine. So I'm going to say fluoride. So I have to fill this in. I got to figure out what magnesium I'm dealing with. So the best way to do that is look at your formula, cut it in half so that all the metal stuff is on one side and all the non-metal stuff is on the other side. These two things added together need to equal 0. So you go from what you know for sure to get what you don't know. So what is the charge on fluorine always? Fluorine is always a 1- charge. That's not going to change. 1-. How many of them do I have? Well, I have 2 of them. So I need to multiply that 1- by 2. So if you're going from here down, you multiply. If you're going from here up, and we'll talk about that a little later, you divide. So I've got a total of a 2- charge, right? 2- charge. So if this is a 2- charge, what has to be the charge over here on the metal side to balance it out? This has to be a 2+ charge. How many of them are there? There's only 1, so I take the 2+ and I divide it by 1, which is 2+, right? So this becomes manganese 2 fluoride. One way to check is to just go backwards. So if this is manganese 2, write it out, manganese, Mn, with, in this case, we're dealing a 2+ charge. Fluorine always has a -1, flip-flop, Mn2, nope, Mn 1, F2, flip-flop works. It's the same formula we started with. We know we did it correctly. So if you go from what you do know to get what you don't know. Again, here's predictable charges, here's varying charges. So how to determine the charge on the metal with a varying charge. Determine the charge of whatever's happening on the anion to get what the cation is, write the name of the cation or the metal, put the charge in the Roman numerals, write the name of the anion and ide it. It's the same system, you just need a Roman numeral in it. So let's try this one here, FeCl2. I'm gonna do it over here. We just got another minute, so I'm just gonna do this one for y'all. All right, FeCl2. So first ask yourself, is it ionic? Yes, this is ionic. And I'm going to put a 2 next to it because it's type 2. Okay, type 2 means it has a varying charge. So it's iron. Write that. I know iron has a varying charge, so I'm going to put a parenthesis. And then I'm going to put the second thing, chloride. I just kind of like to get that out of the way. Now I need to figure out what the charge is of the iron. So I should have written that a little bit farther down, but FeCl2. So first thing we want to do, let's cut it in half from the metal stuff and the non-metal stuff. This whole thing needs to equal 0. What is chlorine's charge? Chlorine's charge is always -1. And how many are there? 2 for a -2 charge. So what does this have to be to balance that out? 2+. And how many irons are there? There's just 1 iron. So we're just going to divide it by a factor of 1, which is 2+. So this is iron 2 chloride. I'm going to do one more really quick while we're here. Question. If it wasn't ionic, would you just leave it the way that it is? We haven't gotten to that yet. If it is an ionic, there's a whole different system, and we'll talk about that next time. So let's do Fe2O. In this one, we have iron, which has an unpredictable charge. And then we have oxygen, which is oxide. So we need to figure out the charge on the iron. All right, let's cut it in half. Needs to equal 0. What is the charge on oxygen always? 2 minus, and how many are there? 1 for an overall 2 minus charge. So what does this have to total? 2 plus. But how many are there? There's 2 of them. So I need to divide it by 2. So each one has a 1 plus charge. Okay, because the total sum of both of these needs to equal the 2 plus. So this becomes iron 1 oxide. Go back and check Fe with a 1 plus charge, oxygen with a 2 minus, flip flop, Fe2O, that is the same formula. You may be thinking, well, I think it's iron 2. I think you're wrong. Okay, well, let's do iron 2 and see if that works. So if you had said instead iron 2 oxide, that would be Fe with a 2 plus, that would be O with a 2 minus, flip flop, we get FeO. Is this the same formula as this? No, doesn't work. Okay, so you go from what you do know to get what you don't know. We're gonna do more practice with that next time, so don't worry if you're like just sort of getting it. We will definitely go over it some more, okay? So we'll stop there. Have a good day. I will see you all on Wednesday. If you have any specific questions, stay around. Otherwise, enjoy the rest of your day, afternoon. Bye, everybody.